In this episode, let's discuss the topic of relativity. Some people may ask why the speed of light is the maximum speed in the universe. Why can't an object accelerate to the speed of light? Today, we will explain this question. First of all, to explain this matter, we need to understand what acceleration is. What exactly is the process of object acceleration? For example, let's consider a box that is initially stationary on the ground. Now, if I want to increase the speed of this box, what do? It's simple. We push it. We apply a force to it. After applying this force, the object will start accelerating, and its speed will increase. If we were to create a table, with time in seconds as the unit, we would see that at different moments, for example, at time 0, 1, 2, and 3 seconds, the object's velocity, measured in meter per second, the velocity would be 0, 1, 2, and 3 meter per second, respectively. In other words, at time 0, the velocity is 0. At 1 second, the velocity is 1 meter per second. At 2 seconds, the velocity is 2 meters per second, and so on, continuing in the same pattern. So, this object is accelerating, and we can define a quantity called acceleration. What is acceleration? Acceleration, denoted as a, is the rate of change of velocity with respect to time. Let's see. For every second that passes, the velocity changes by 1 meter per second. So, the velocity change is 1 meter per second, divided by 1 second, which gives us 1 meter per second squared. This is what we call acceleration. Acceleration is the rate of change of velocity with respect to time. For example, we often talk about gravitational acceleration. What is gravitational acceleration? It refers to the acceleration experienced by an object in free fall. Gravitational acceleration is denoted as g, and is approximately 9.8 meters per second squared, meaning that for every second that passes, your velocity increases by 9.8 meters per second. This is the meaning of acceleration. Now, how do we calculate acceleration? This brings us to the second concept, which is Newton's second law. Newton stated that acceleration is related to two factors. The greater the force you apply, the faster the object accelerates. However, if you apply the same force to push a box, the heavier box, the slower it accelerates. For example, if you apply a force to a small bicycle, it quickly accelerates. But if you apply the same force to push a train, you can imagine that it's difficult for the train to accelerate. Its speed change is slower. Newton's second law tells us that the acceleration of an object is equal to what? It is equal to the net force acting on the object divided by the object's mass. In formulaic terms, it is written as A equals F divided by m. The greater the force acting on the object, the greater its acceleration. However, under the same force, the greater the mass of the object, the smaller its acceleration. This is what we call Newton's second law. So, with the same force, the acceleration of different objects with different masses will be different. In classical situations, if the mass, m, remains constant and the force, F, remains constant as well, it would result in a constant acceleration, a. When acceleration is constant, it means you can continue to accelerate. So, in classical situations, how does your velocity change over time? It changes like this: the longer the time, the greater the velocity. Or it changes in such a way. These two scenarios correspond to having a large acceleration and having a relatively smaller acceleration, respectively. But regardless of the situation, you will continue to accelerate in this way. That's the classical case. Now, let's discuss why in the context of relativity, objects cannot exceed the speed of light. In the context of relativity, Einstein's theory of relativity has a conclusion that the mass of an object changes with its velocity. The mass of an object is equal to m0 divided by the square root of 1 minus v squared divided by c squared. m0 is known as the rest mass of object. In the relativistic mass formula, m represents the mass of object in motion. It refers to the mass of an object when it is in motion, which varies with its velocity. In the formula, v represents the velocity of the object, and c represents the speed of light. The speed of light, denoted as c, is a fundamental constant derived from the basic assumptions of Einstein's theory of relativity. With this formula, we can observe that as the velocity, v, of an object increases, the denominator of the formula becomes smaller. As a result, the relativistic mass of the object increases. So, there is a fundamental conclusion that a moving object has an increased mass. If an object approaches the speed of light, what are the consequences? If the velocity approaches the speed of light, v divided by c approaches 1. Therefore, the denominator approaches 0. Therefore, the mass would become infinite. With the denominator approaching 0, the mass becomes infinitely large. So, what does this mean? Let's go back to Newton's second law. In the context of relativity, the form of Newton's second law does change, but for now, let's use the classical form. According to Newton's second law, acceleration, a, is equal to the force, F, divided by the mass, m. Assuming the force remains constant, but the mass becomes larger, the acceleration becomes smaller. If the mass approaches infinity, the acceleration approaches 0. In other words, as an object's velocity increases, its mass becomes larger, and its acceleration becomes smaller. Ultimately, the object's velocity cannot reach or exceed the speed of light. If we were to plot a graph, it would look like this. The acceleration decreases gradually over time, slowing down more and more until it eventually levels off. At this point, the velocity reaches a constant value, which is the speed of light, denoted as c. In other words, it is not possible to accelerate an object to a speed greater than the speed of light. The reason for this limitation is that as you accelerate an object, its mass increases, causing its acceleration to decrease. Ultimately, the object can only reach a maximum speed equal to or less than the speed of light. Thank you for watching this episode. See you next time.